All right. Let's look at operators with continuous spectra. Okay, so here we are going to have again an operator Q, but this time it's going to have an eigenvalue which we'll call perhaps lambda Q again. So something like this. Okay, so it's just like the expansion that we are using here, except that I am using the variable Q instead of n, because n is a signal for change in terms of discrete quantities. So this is lambda Q f Q of x. So Q is now a continuous variable, okay? And being continuous variable, it can take some set of real values. Okay, so the various properties that we have shown here still go through, except that their form becomes a little different, okay? Instead of the Kronecker deltas, we are going to get, okay, so if I have some fq1 of x, fq2 of x, if I take the complex conjugate and integrate this over all x, now instead of the Kronecker delta, I get this Dirac delta, q1 minus q2. Okay, and again, the expansions and things of that sort just work out as usual. So if I am, for example, trying to expand this psi of x in terms of a set of fq's, so I am going to get now this functional form. Let's give this some other, well, maybe we'll just call it c of q, okay, instead of cn. And these fq of x's dq, so it's again an expansion of the same form. And how do I find what these expansion coefficients cq's are? Exactly the same procedure. Okay, I multiply left hand side by, say, some fq prime of x with a complex conjugate, psi of x dx. So that generates now another integral on the right hand side. So I'm going to get this dq integral is still here, cq, but I now also have a dx integral with fq prime of x complex conjugate, fq of x, okay? And this thing we decided was going to be equal to delta q minus q prime. And again, whenever you get a delta function integral like this, you just remove, okay, the remaining integral or one of the remaining integrals and just put in q equal to q prime, okay? So this is going to just give me c of q prime. Okay, so I have determined what the expansion coefficient is going to be. But let's do the exercise which involves, again, the normalization to see where that leads us. Okay, so let's see. Okay, so again, I want this thing normalized. So psi star psi dx is going to be equal to 1. Now I want to use this expansion in my okay, equation here. So the dx integral is still here. In place of psi star, I'm going to put this in. So it's going to be dq, okay, c q star and f q star of x, okay. So I have taken care of the first psi. Now I have to do it for the second psi. So that's going to be a different integral, okay, dq prime, c star, no star anymore, c q prime, f q prime of x and dq prime I have already written. Okay, so that's my integral now. Now, again, if you just look at this CQ star, oops, I'm marking the wrong thing, sorry. FQ star, FQ, and dx, that's my delta function, okay? That's how the delta function is defined, so that's going to give me a delta q minus q prime. Okay, so let me just use that to eliminate the q prime integral. And wherever I see a q prime, I'm going to write a q. Okay? So what is remaining? I have evaluated the x integral and obtained the delta function. I'm not going to write the q prime integral, so the only integral that remains is the dq integrals. And I just have c star of q, c of q. Okay. Now, what is this? How do we interpret this? dq magnitude of cq squared. And all of this is now equal to 1, you see. So how would I interpret this magnitude of CQ stuff? Okay, probability. So this is a probability density function as a function of this variable, okay, continuous variable Q. Okay, so if this is, for example, for the momentum, I would say this is the momentum space wave function, okay, because this psi star psi, remember, is the probability, okay, as a function of x. So I would call it px of x. So this is now a different function, obviously, but it's a probability with respect to the q variable of q. Okay, so it's a, so this cq is a probability, okay, it's a wave function in this q space, which leads to a probability density. So you see, these things I can write in x space, which was the natural point to start from. Okay, we started from position space and wrote down these wave functions and everything. But the argument is valid really for any eigenvector of a Hermitian operator. Okay, so we'll now be looking at this picture from a more general perspective, not necessarily only from the perspective of the position space. Yes.
I was wondering about how did we do this second equation, Dirac delta function?
This one? Okay, no, this is the normalization. Okay, so this, if I had, remember that, okay, I may have erased it, but for the case of, okay, discrete spectra, I have q fn equals lambda n fn, and the normalization condition was fn star fm, okay, dx is delta nm. Okay, so we have these for discrete spectra, For continuous spectra, this, okay, goes to that, this goes to that. Okay? Yes?
An operator is going to have a discrete spectra rather than a continuous spectra.
You just have to solve the problem, and depending on the boundary conditions, okay, you either get one or sometimes you get a mixture. Okay, we have not, so let me just open a parenthesis here. We have not discussed the problem of a finite valve. Okay, so this is in your textbook. I did not go through it because it's mainly a little bit too, well, the discussion depends on lots of graphics and things of that sort. So if you look at the energy spectrum here, this is going to have bound states. Okay, so if you look at the energy scale, the energy eigenvalues, you are going to find a number of, okay, discrete energy levels. But then once your energy exceeds this level, which extends all the way to infinity, okay, so I have these discrete points, but then over here I have, excuse me, I have a continuum. Okay, so the energy scale in this case, for example, is both discrete and continuous. Okay, so it depends on the excuse me, it depends on the boundary conditions on for various energies.
And if you try to normalize, you both have a sum and an integral?
Yes. Okay, so in that case, if you want to expand a general wave function, this psi is going to have an expansion Cn in terms of these discrete Fn's, but then there will be an integral which corresponds to, okay, whatever C of q, f q of x. Okay, so two types of functions corresponding to discrete and continuous. Okay, for that. And but you can sort of see that if you have a general psi which looks something like this, it will mainly be, okay, expanded in terms of these discrete states, because there's no part of this going to infinity. These functions will not give you any contribution. But if you have something over here, okay, perhaps a Gaussian approaching this well, then in that case, the expansion will practically contain only these, okay, because the others will not be valid. Okay, other questions? Okay, so this problem is in your textbook. Let me assign it to you as a reading assignment, okay? Just go through it. It's not a difficult problem, but contains some algebra. Yes?
Can you repeat the part about the Gaussian?
About the?
Gaussian.
Okay, so I have to do an expansion like this, right? And then if I now want to expand this function in terms of these functions, remember how we do it, okay? In fact, it's right over here. We take this wave function and we multiply the wave function with the eigenstate. So when I multiply this wave function with the bound state wave functions here, there will be no overlap, right? I'm going to get zeros for these coefficients, right? Because this Gaussian will be somewhere over here, and these wave functions corresponding to bound states will be over here, okay? So there will not be any overlap between them, so these Cn's will turn out to be zero. But these FQs, which are the extended energy eigenstates, they are extending from minus infinity to plus infinity, they will have some overlap, so you are going to get finite contributions for the CQ, okay? If you have a general Gaussian which covers also this, then of course it will be a mixture. Okay, but usually that's not what you want. Other questions? All right, so where are we? So again, the coefficients here, the coefficient functions in this case, not discrete coefficients, but these C of Q's now form a wave function for this type of measurement, okay, this Hermitian operator. So the Hermitian operator is associated with the measurement, and whatever this Q is, okay, that is now a continuous variable, and I'm going to get a possible different results for that. Okay, so we have already done the momentum eigenfunction, so let's just look at that. Okay, so as an example, in fact, we have just seen two, so let's just look at both of them. We have seen position, and we have seen momentum. Let's start with momentum. Okay, so the momentum operator is P. We saw that it's Hermitian. So it's going to have eigenstates which look like what? What are the eigenstates of momentum?
E to the I pi x.
I kx, okay. So e to the I kx. And to be properly normalized, I need a 1 over square root of 2 pi here. Okay? So P times that, you see this is now my eigenfunction. Okay? So if you like, this is fk of x. What does that give me? Well, this thing here is h bar over I del x. So it brings down an ik. I's cancel. I have an h bar, so I get h bar k times e to the I kx. Okay, so this is over square root of 2 pi. So this is an eigenfunction, you see, of the P operator with eigenvalue h bar k. Okay? So everything is nice. Now let's just check whether these things are correct. Okay? So if I take this object, find its complex conjugate, so let me just write it over here, fk star of x, fk prime of x dx. Okay, so these are two different eigenfunctions integrated over. So what is that? Well, 1 over square root of 2 pi from both of them gives me 1 over 2 pi. Then it's going to give me e to the I x k prime minus k dx. And indeed, the inner product is delta k minus k prime. Okay, delta k prime minus k and delta k minus k prime are the same because delta function is an even function. All right, I can expand my psi of x okay, in terms of, okay, so this is the coefficient object we called g of k for the momentum case. I can expand my psi of x in terms of these fk of x's, dk, right? I'm integrating over these states. So I'm going to get g of k e to the I kx dk, okay, minus infinity to infinity, divided by root 2 pi as my expansion. Okay. So this is now my expansion in terms of momentum eigenstates. All right? And we know how this works. This is the Fourier transform, so we know how to find what g of k is and such things. But of course, what is interesting is now if I take the magnitude squared of this eigenfunction, so g of k over root 2 pi, magnitude squared is what? What the physical interpretation? Yes, it's the probability density. Okay, so if you like, this is probability with respect to the k variable of k. So this is the probability density with respect to the momentum variable. Okay? So g of k, so this thing here, g of k over root 2 pi, we call it the momentum wave function. Okay. Now, finally, let's come to position. In fact, usually, although we have been working in position space for such a long time, since we do not know that we are working in position space, we just put psi of x here, so we are like the fish who are not aware of the sea. Okay, so when we start doing these things for the position space, sometimes it looks confusing, but it really isn't. It's just position space is just a space that is associated with a Hermitian operator. So what about position? Okay, position operator, let me make it a capital X. So what is the eigenvalue of the X operator? Eigenvalue, eigenvector. If I want to make an X measurement, you see the eigenfunction of the X operator must correspond to a measurement that's definite. So it will give me, it will correspond to a particle definitely at a certain point. So what does that sound like?
Impulse.
Pulse.
Yes, okay, so if I have, for example, x delta, so this x is no different than ordinary x, okay, so but it's the x operator, x delta x minus, say, x prime, okay? That is going to be equal to x prime times delta x minus x prime, right? So x here is my variable x, but you see this left-hand side is 0 unless x is equal to x prime, right? So it will be equal to the right-hand side. So I have the general x variable here. X prime is a certain point where the particle is definitely at. Okay? So this says the particle is definitely at x prime because this is now my eigenvalue. Okay, so this is my eigenvalue. Okay, this stuff here is just the eigenfunction. Okay, and this is the operator. So is this clear? Looks perhaps a little confusing at first, but okay, that's what it is. X times the eigenfunction is equal to x prime, the eigenvalue, times the eigenfunction again. Now, this corresponds to a certain particle at x prime. And here's my general psi of x. I want to expand it in terms of these eigenfunctions. How would I do it? Well, I will need some set of coefficients corresponding to each x prime. Okay, so I want to integrate this over all eigenfunctions at various values of x prime. And that corresponds to, okay, so the eigenfunction is delta x minus x prime. So these coefficients, when I integrate it over, is supposed to give me psi of x. But what is that coefficient? What can I put there to get psi of x?
Psi of x prime.
Yes, okay, so psi of x prime is in this case, okay, because this case is special, I am already in the position space. These are the expansion coefficients. Okay, so what does that imply? This psi of x prime magnitude squared is the probability x at x prime. But that's something we already know, right? That's this x object. We have been using it all this time. We never really looked at it from this perspective. Okay, we didn't look at it as a combination of lots of delta functions, and each delta function at that psi of x. But from the point of view of being an operator, and eigenstates and eigenfunctions, the position space is nothing special. Okay, it's just the same as as any other Hermitian operator which corresponds to a measurement. Yes.
Also, I couldn't understand that how we can determine that the eigenfunction of the x operator.
Okay, x times something is equal to some eigenvalue, which is going to correspond to a definite x measurement, times the eigenfunction. Okay, and this satisfies it. So I just gave you the solution. Okay. All right. Let's just check certain things like orthogonality. Right. Do I have a relation here for orthogonality? It's actually quite simple. All right, so let's just also look at the orthogonality. Remember, we decided that for continuous variables, we had this fq star of x, fq prime of x dx was going to be equal to delta q minus q prime. So if I just apply it in this case, this is going to be delta x minus, say, x prime, a certain point, and then I have delta x minus x double prime. So this is the eigenstate for x prime. This is the eigenstate for x double prime. And when I integrate with respect to dx, again, since this is a delta function integral, I take one of these things, okay, it doesn't really matter, and remove the delta function and the integral and put x prime wherever I see an x. So this is going to be delta x prime minus x double prime. Okay, so indeed the orthonormality is also satisfied. Okay. All right. So, how much time we have? Good. Having gone through all of this, you see, since this leads to such a general approach to operators and eigenfunctions and eigenvalues and such things, we'll now start to look at the quantum mechanical problem from a different mathematical perspective. Okay. So what we'll do is we'll define a new type of space. Okay, it's called the Hilbert space. Okay, can you put your phone away, please?
All right.
Okay, so we have the Hilbert space. The Hilbert space is a special type of space in which special type of vectors live. The wave function, for example, that we have, psi of x, will associate with a Hilbert space vector. Okay, so I'll just put a capital psi like this, and I'll put this notation around it. Okay, so this just says this is a, okay, this is a vector. Now, if I have a second vector, suppose I have also a phi vector, that's going to be something like this, phi, that, okay? So I can define anything I like, but what's the use of this, right? So in this Hilbert space, we'll see what its components are, okay? These things are two vectors. This is our vector psi, and that's our vector phi. Now, we define the inner product. Okay, so the inner product of phi with psi. Okay, so this quantity is now called, okay, the inner product of phi and psi. This is defined as, put it over here, the integral of psi star of x with psi of x dx. Now, how do we associate the concept of a vector with this? Okay, this is somewhat dangerous discussion, but let me just try to give you some intuition. This psi vector, you can sort of imagine until your abstraction builds up as a huge vector whose components are psi of x1, psi of x2, psi of x3, etc. So these are the values of psi at various points in x, except that, remember, this x is a continuum. Okay, so since this is a function, it's an infinite dimensional vector. Not only is it infinite dimensional, the dimensions form a continuum. Okay, so it is something really quite weird looking, but it's very useful. So the terminology is that if I have something like this, okay, this piece here is called a bra vector. So this piece is called a ket vector. So this thing you can call C if you like. So this is terminology invented by Dirac. So this is also called Dirac notation. Okay, just a way to represent these things. So you can see that if this is to be the inner product, and if I want to speak in terms of vectors, the bra vector is something which looks like, okay, phi at x1 complex conjugate, phi at x2 complex conjugate, phi at x3 complex conjugate, etc. So when I form the inner product, it is just the multiplication of those terms and summed over. Okay, and since it's a continuum, it corresponds to an integral. Okay, so every function, every complex function has its, okay, position inside this space. Now I have written these things in terms of x1, x2, x3, x4 vectors. So those are its components, right? So what does that mean? What are the these directions that are, okay, making up this space? Well, we just said there are infinite number of them, and they also form a continuum. But you can see that the individual unit vectors, if you like, that make up this object are things like x1. Okay, so what is x1? x1 is going to be a vector which looks like this, okay? 1 here, zeros all over, okay, which, and this point here corresponds to x1, okay? x2 is a unit vector in the direction x2. So this is something which looks like, again, okay, it's impossible to obviously draw these because these are actually a continuum, but this one only in x2, okay? So I have a whole bunch of these things, okay? This is x3, x4, etc., but an infinite number of them. So it's an infinite dimensional space, and this is my vector inside it. If it is normalized, then its size is equal to 1, right? Because then psi star psi is going to be equal to 1. All right? Okay, so the operators, let me just erase this. Operators, okay, are objects in the space which transform one vector to another. Okay, so if in real space I have this function g of x given to me by some operator q operating on f of x, okay, in Hilbert space, this is my Hilbert space, so I'll do that to show that it's Hilbert space. The function f now becomes a ket vector f. Function g becomes a ket vector g. And the object which takes f to g is q, but since it's in the Hilbert space, I'll put a hat on it. At some point, I'll drop the hat, but so our notation will be that for this case, g is equal to qf. And now we can write down many of the things that we have been writing down in this notation. For example, what is the expectation value of operator q with respect to wave function psi? Well, I need to have an inner product, okay, of, so first let me write it in our ordinary way, psi star q psi, right, dx. So I just told you that q acting on psi can be written like this. Then I find the inner product of that with psi. Okay, so in the Hilbert space, it's going to give me psi, okay, q acting on psi. Okay, so q acting on psi, and then I have the bra vector, okay, that's over here. Okay, so this is, of course, now the operator with that hat. It's the same operator, but it's in the Hilbert space. Okay, so if I want to write down, for example, the expression for the Hermitian adjoint, how do I do it? I have this operator Q acting on psi, and phi on the left-hand side is going to be equal to what?
Inner product.
Psi, okay, Q dagger, this is the adjoint, phi, I'm going to get a result out of that, but I have to evaluate a complex conjugate. Okay, so this is now going to be my expression for the Hermitian adjoint of this object. Now I have this complex conjugate here. Okay, so in general, obviously you get a number out of this, right? The inner product itself is just a number when you do this integral. But you can easily see that okay, so let me open a parenthesis here. Remember that inner product of phi with psi is integral phi of x star psi of x dx. If I do it other way around, if I do it psi phi like this, then it's going to be the other way around. So it's going to be psi star x phi x dx, which means this is the complex conjugate of the other, right? So phi psi, okay, is the complex conjugate of psi phi star, okay?
May I add a small
Yes.
Remark or
Yes.
warning about notation?
Yes.
In most math textbooks, in most textbooks written for mathematicians, psi products in phi product psi, it's written integral phi times psi product dx. So inner product is linear in the right and antilinear in the left, as opposed to Phys notations where it is linear on. Sorry, I meant the linear on the left and the conjugate linear on right.
Okay, good remark taken.
And sometimes it causes a lot of confusion when you read another textbook.
Okay, so it's a good idea to stick to physics textbooks. Sure. Well, we shouldn't really take it that. This is, of course, Dirac notation, but of course, Hilbert is the person who should get lots of credit for this stuff. In fact, it is interesting reading. Again, Hilbert's story is quite interesting. He worked on some very important problems, not all of them successful, but still quite remarkable. Okay, so how are we doing on time? Okay, maybe I'll stop here today because I don't want to go into the next topic. So I'll let you go 5 minutes early and we'll see what we can do next time.